and let's hear our story about the Kalman filters.
Hello, everybody. So, welcome to my meeting, and we invited a special guest called Sergey. So, you're gonna say few things. Yeah, this as much as people want. Yeah. All right. So about common filters. This is deep common filters. So I'm going to talk to you about what common filters is and why we care about it, and then why we think that deep learning might be a better fit for some systems at least. So NASA, trying to take people to the moon. Very ambitious. I believe I can fly. Send some innocent children to space. And the thing is that, once you get people out in space, you have to know exactly where they are. Otherwise you don't want people getting lost in space. You're trying to get to the moon and then they just get closer to the sun and just burn. You don't want that. We want to measure precise location, right? Position, at least that's one of the things. Um, the thing is that, well, we're humans, we build machines, we're not perfect, so our machines can only measure things as well as we can make them, and as well as the universe will allow us, I guess. And even if we could make precise measurements, there are things like lunar gravity. Like, there are things in space that can shift, things.
Still a problem.
Yeah, it's still a problem. So it's like, that's hard. But it's NASA. So I try to see what they can. Measurement noise makes it hard to define exact location. There's a space we don't want any slight shifts might cause very huge movements around. You don't want that. So the top is ideal. That's what we learn in textbooks, physics textbooks. Like, okay, we've got a rocket, it's going to the moon. Woo, go straight and then gets there. But that's not true. That doesn't really happen. You get things moving around with some noise. And replace Albuquerque with space.
Albuquerque is totally appropriate,
Alright.
at least for this meeting.
Okay. So the thing is that we're definitely going to measure the position, right, of the spaceship at each point in time or specific intervals, right? Because we're measuring. So there's always like you have to measure specific intervals. We call it sampling time. And the measurement itself could be noisy. We call the measurement, of what we care about, the observation, right? And the true thing that we want, is what we call the latent space. In this, I do realize that the latent space term, the latent, is being used in deep learning papers a lot. In physics, electrical engineering, we just use state variables without the latent. I don't know why. So I remember that the first time I heard it was I think it was one of Deloitte's presentations, and I was like, what's this latent thing? It's like, no, it's the same thing. The state variable. It's like, oh, okay. So I don't know why it's called latent.
Because they're unobserved.
Okay.
They're not directly measured.
Okay, I get what you're saying.
You're measuring something, but you're measuring the noisy thing.
Mm-hmm.
But there's like latent variables usually that are not observed.
Oh, okay. Fair.
That's
That's what. Okay.
hidden markup models.
Right. Okay.
Same.
Fair. Fair. Okay. Okay. Yeah. So you can see that the true trajectory is the green, and the observed measurements is the red. It's all over the place. You're measuring things. It's there, but it's messy. You're not exactly sure. And a common filter is it starts with an initial rough guess, and then it kind of follows the true trajectory quite closely than the noisy estimation. So that's why we care about it. This is a the this is how the model looks like in typical physics classes. It's you have the x, which is the state in the latent space, the latent states, and you have a, which is transitioning that state. So for instance, you have a let's be more into it. We have a car that's moving right at time t1. The car is at a speed of 20 it's at a speed of 20 meters per second, whatever. Miles per hour. Yes, for the United States, miles per hour. So we have a car that's moving at T1, it's 20. All right. At T2, you would guess that if you move into T2, it's gonna have some dependence on T1. You can't. It's not. It's almost impossible if you have a very short time measurement. It's impossible to get, let's say, a speed of 100 if the previous one was 20. It goes, right? So the A just tells you how it transitions, how that state that you care about, the speed transitions from one to another to the next. That's what the A is. And the B is a control, which just means that, well, you have a car, it's moving, what controls it? That's the way it is. So the more you press, you hit on it, the more you go faster. So it depends on that. And the B is just telling you how that translates to the state. So how does the steering wheel affects the position of the car, the speed of the car, stuff like that. So that's what the U is. And so once you get, so you can propagate the system, you have these variables, you can estimate what that state is going to be at each point in time, and then you project what's the name, an error covariance. That just tells you how wrong do you think we are, you know. And then once you get that, you compute something called a Kalman gain, and the Kalman gain tells you how confident are we about what we observed, right? That just tells you how confident we are. And then you update right here, which is just to be based on the Kalman. So if we're very certain, like if you're all very certain that what we measured is correct, Kalman gain is going to be 0. So it just gives you the exact same thing. So you just update it based on the Kalman gain, and then you update the error covariance again, and then you go back and keep doing the whole process.
What is ZK? Z sub K?
Sorry, remind me.
Z sub K?
I cannot see.
It's
That's the error at time point K, right?
Sorry, can somebody point to it? I'm so blind.
What is this?
I forgot.
But just tell it.
But that?
Just tell what it is. I mean, I'm just wondering.
No, I don't. No, I don't remember.
Oh, you don't remember?
Yeah,
Okay, well,
it's been a while.
it's like,
I don't remember.
what is it?
Is the output. So at each point we have the measurement, right? Which is like the Z, the what you're measuring from. Say if you have it, whatever, what the output that you're measuring from, fMRI, the output. So the X is the internal state that you don't know, that you're trying to figure out, right? So that Z is the output. Yeah.
Okay.
Yeah.
Z is the measurement.
Yeah. So typically, I like to use the Y for the output. So I got confused when, because this is from the paper, so they use Z for that, and then they kind of mix it up sometimes. But yeah, that's what it is. All right, going. So this also is usually done in a real time system. Like you can do. They have a weird thing. If it's offline, they call it Kalman filtering. If it's online, they call it Kalman STB. I don't know what's going on. They're just trying to name things differently. All right, I'll go back. As you can see right here, we have an A matrix that linearly multiplies with the state, right, at each point. And then you have the control, the B, the control matrix B, which linearly multiplies with the control unit, the input. And then you have both of them. You're assuming that the control linearly affects the state, and you just added them. So it's like it's linear all over the place. But the world is well, linear is fine, but like they always say that like maybe Sergey can tell us his success story, and when he was talking to us, you were not here.
I was there.
You were here, okay. When everybody would Vince and Sergey and Army, Gene were talking about how they've been doing the research and how they got here and all of that. Everybody had very crooked stories. So life is not, we don't, we've got very weird, non-linear things happening everywhere. Like real patients, disease progression is really linear. Like I have still not found any study that has found, any cross-sectional study that has found linear relationship with any form of dynamical measure that you could come up with drug brain modulations. I've still not found anything. And I checked on I used deep research from ChatGPT to check to see if it's actually true. They said it's usually longitudinal studies that find them and not cross-sectional. So we know that and we also know that it's not linear. Like for instance, you might be giving somebody a dose, right? But after you hit a certain threshold, it doesn't the effect doesn't do as much, right? It just plateaus. So there are a lot of things going on. It's not linear. So the typical Kalman filters might not be very useful for things like that, right? So here, deep Kalman filters, all it does is it just replace the static terms, the A matrix, the B matrix, with a function. So you replace it with a neural network. So you replace the whole A progression and the B progression, right? So you have a function that changes, that depends on the state, and then the control. And time, if the system is a time varying system. So for instance, for us, we know the fMRI signals are time varying, it's non-stationary, phase is changing, frequency is changing with time, everything is changing, all over the place. So we can add a T in the function. So the deep neural network learns that the function changes with time as well. Yes.
Couldn't be any function, or do we have some limitations of the deep Kalman filters?
The function though would be a neural network, right? The
If
parameter.
we assume it's a universal function approximator, then it'll figure out. It never does, but
Is it going to be online?
yeah, it's recorded.
Online.
That's okay.
Okay.
We're very informal. Thanks for people. If you have more questions on you.
All right. So what the model predicts or brings out is a mean and a variance, which is kind of intuitive because it's more like you want to know you want to know the best prediction of what the internal state is, right? But you also want to know how sure you are because you're not exactly sure. So you might want to know that as well. So the model predicts a mean, right here, and then a variance, which tells you how certain we are, right? So on average, this is what we think it is, plus is how certain we are. And then the model is using the input, it's dependent on the previous state that we estimated and then the previous control. So here's a problem. For example, we have a patient. We measure some things like blood sugar, cholesterol, blah, blah, blah. But, we don't really care about that. We care if the person's disease is progressing or what organ functions, like how the brain works. And that's what we want, right? We want a model that tells us that. So we never see the true state. We don't know what's going on. We can only observe. That's all we can do, right? But now here's the thing: we want to build a model that learns how the hidden states, what we care about, causes the observation. How are things like consciousness causing the blood to flow, something like that. That's the kinds of things that we care about. What might the hidden states be given the observation? So, for instance, we want to know what the hidden states themselves are as well, right? Not just how it informs the observation. Here, the learning is done by creating two models. We have a recognition model, which is like, what it does is that it's basically given, and here's where I use the Y as instead of the Z, because I was writing this and I was like, I want, yeah. So Y is the observation and X is the state, the latent state. So given a Y, can we guess an X that can map to that Y? That's basically what that recognition model does. And then if the guessed hidden state, the X that we guessed is really true, then it should give us the same observation that we saw, right? So that's what the generative model is. Here,
there are complications.
there are. Can you tell me about it?
There are many models in which the same solution, the same observation can be generated by multiple different internal states. There might not be one-to-one from state to observation correspondence. And
given the same inputs?
Given the same Y, given the same X, you get the same Y.
Yeah.
But given another X, you also get the same Y. And there's a set of X's that will give you the same Y.
But are you isolating the control unit, the U? Are you saying that if you give the same, because the X and the Y is not mapped independently, right? It also depends on the U.
Yeah.
right? Which is a control, like
Yeah, I don't know. It depends on the system, which
Right.
kind of system is.
Right. Oh, you're saying that the
stuff like
the-
but in general,
okay, okay, yes, definitely.
you may not be able to
Yes, I agree.
invert the system. This
Yeah.
is more of like, okay, it sounds to me like the Bayesian inversion. Yeah, apply Bayes theorem and you'll get your Q from P, or vice versa, right? But it's not generally solvable.
Right, right. No, they
It's
mentioned
just
something I didn't even understand. I was like, okay.
I mean, it's a problem in MEG, EEG,
Okay.
what is it, geophysics, I forgot the seismology,
Mm.
things like that. Where,
How do they use it in geophysics? It's like predicting the center of the Earth or what?
well, you have a lot of seismographs on the surface, but then your task is where did it happen? Like, if you knew where it happened, you know what seismographs will do easily.
And then and then you can plug
inverting it, there can be many solutions that would fit the seismographs.
Yeah.
Sorry,
That's true. So, I mean, more intuitive is like if yeah, it's I understand what you're saying. So like more intuitively, it's like if you yeah.
like in simple
yeah.
Gaussian linear Gaussian model of Kalman, there probably is one-to-one correspondence.
Yes, yes,
right.
yes, there
It's
is.
like one. Since you're going in general, you're throwing a general function. It also depends on the properties of that function, right?
Yes.
The null space, etc.
Yes.
It may be collapsing stuff, such that it's not distinguishable anymore.
Yeah, I agree.
I assume.
So here they do evidence load bound. Is this something that is used like a lot? I don't know in deep learning, or is this new?
Yeah.
Oh, it is
It's
something
used,
there.
it's used a lot in variational encoders, just to be and I mean in deep learning, I'm not sure EM algorithm works just like that. Right? It's
Alright. So they use they try to find how well does my guess, explain what I saw. So that just like what I was explaining to you, that we have you guess an X and you try to see how it maps, and then you have an you guess an S and you try to see how it maps to the observation, and then they do KL divergence just to find the like the distance between how you warp one distribution to another. How weird is my guess? So the thing is that I remember I'll talk about this a little bit from like your Pablo's stuff. So like you want good predictions, but you want predictions that make sense in a way that explains it. You cannot have highly transient changes depending on if you understand the system. For instance, I mentioned that if you a time 1 second and then your speed is at 20 at time at second 2, it's very probable that the speed of the car is going to be 100 because of how cars work and the cars that we have and all those kinds of things. So you want something that makes sense based on prior predictions, not just there, right? So that's what that part, how well does my guess compares to prior belief. And here they try to do this thing where they map the deep Kalman filters back to the classic Kalman filters just to kind of make sure that it's trackable. We know what it is, and because we always want to try to explain deep learning models as much as we can. So let's try to map back. So here essentially is that I told you that we have the mean, it spits out the mean and the variance. And again, the mean depends on the state, right? Which is X, the latent state, and then the U, which is the control unit, right? And time, as I mentioned, right? Because so the image is changing with time, it's changing with the state, and then it's changing with the control. And then here we have the state transition covariance, which also means the covariance changing with those three things as well. Now, if we set that state transition mean back to AX and BU, and then we set the state transition covariance back to a single covariance matrix, then we get the typical Kalman filters back, the linear Kalman filters back. And by the way, there are two main different kinds of non-linear Kalman filters approaches to this one, extended and this one ensemble. They don't really talk about it so much in the paper, but I think that the model, the deep learning model is not so different from one specific one, the ensemble one. It was just just to say. So here for the training, they try to maximize the L below lower bound. The first term is reconstruction accuracy. That's if this was a hidden state, if this is a guess hidden state, how likely is how likely is the actual observation? And then the KL terms is just penalized as my guess of hidden state compatible with how the word works. Does it make sense? So here you can see right here. It's hard to get my cursor to move around. Okay. So right
You
here.
need a color.
Yeah.
No, but that's exactly.
No, yes, I do. Yeah.
You have a noisy observation
Yes.
and hidden
You
state.
can predict where it's gonna be, so I don't have to keep moving around. So right here you can see like this KL part, you have X again. You have X of T, right? Give it X T minus 1. And you can keep going. T minus 2, keep T minus 3, T minus 4. You're trying to see it shouldn't be so different from the previous states. It should move, but it should not be entirely different. So you try to penalize it so that it stays within the boundary of what you think that system should look like. Right. Here, the training loop guesses the hidden state using the the recognition model. It uses the generative model to generate the observations, just check to see if they actually match. And then the gradient calculation using the elbow loss, and then they update all parameters using that. They use 4 different models for recognition. They have Q, I think, independence, and Q, I forgot what the LR means, and Q recurrent neural networks, and then QBRNN is bidirectional recurrent neural networks. So you have MLP, RNN, and then RNN. And you can see for the first one, the independent just looks at the time point and then uses that to predict just that in that state. So it's like, I mean, if you were to guess, you guess that that's going to be the most noisiest, that's going to be the most unreliable, because it doesn't care about what the system is. It just cares about, let's try to get the best approximation of prediction at that time point. So it's too noisy. If there's noise in the measurement, you just get that, right? And the LR, which is NLP, uses the previous state. So it just takes the it takes the previous state, the current state observation, and then the future, one point in front of it. So it takes 3 with the actual in the middle, and then uses that to predict. And then we have the recurrent neural network, which uses all previous ones, right, to predict. And then we have bidirectional, which has everything. So the bidirectional can only work offline because you need to have the full sequence to be able to do it. Right? And usually people like to. One of the cool things is that it's an online approach for correction, right? So the recurrent neural networks kind of makes more sense to me, at least. Right, and here I want to ask, so for Pavel, what you are like working on is my understanding of it is that you do just X of T, sorry, Y. I think you do more of the QLR without the YT plus 1. Am I right?
YT is a signal and text, yeah.
Yes. YT is the observation, the bold signals that you have. Right, and XT for you, you're not getting XT. You're just getting the function and using the functions stuff, time, temporal things to figure it out.
To be honest, I think I'm closer to 1.
You're closer to.
Yeah, except I'm using not YT and not UT, but T minus 1.
Yes, you're using T minus. So you're using T and T minus 1. Yes.
Oh no, actually I'm using YT.
Yes, you are using YT. Yes, so it's YT. You said okay. So yeah, so you're using YT and then YT minus 1. Because YT depends on YT minus 1. Yes, yeah. So it's more similar to the QLR. All right, the setup, we have torch, PyTorch, Adam, we spoke about these things as a toollet, STM, and dropout is 0.1, and training metric is slow. Okay, the dataset that they use is a synthetic dataset inspired by robot medication and medical complexity. We have MNIST, they get images, the actions is the same as the control. So like you have a car, it's moving, you have the steering wheel, so you have rotations. You can rotate the number right, rotate it left. Just like a treatment, like you give somebody more doses, you give someone less doses. You crush the pills, you don't crush the pills, stuff like that. And observation is the rotated noisy images, and then we have these three square element patches in the corners that doesn't depend on the action at all. So like somebody, has schizophrenia, trying to give the person drugs, and the person gets flu, for instance, which doesn't have anything to do with schizophrenia. It's just the person just got flu. So they kind of try to mimic that kind of process, and then you add noise to it, just to give process noise. Yes. So I did explain that. So yes, that's about it. And here is one of the results we have. See, so I'll take you through it. The first one is the training. So here we have R. The R is the mean reconstruction, and the TS is the training sequence, the input. So the model sees TS, right? I don't know. I kind of feel like they should have flipped it. Like I feel like TS should be first, and then R. It was weird trying to figure this out. So TS is the
Start from the bottom. Then
yes. Okay. Start from the bottom, then it makes sense. Yeah. So TS is the noisy figure, and then they try to predict with R. Sorry, they predict with the model and to get out R.
I'm surprised how sharp the squares are. The filtered out, the clean
Yeah.
square. They're super sharp.
Well, it's the mean. So you think it's too clean?
Yeah, I mean, look, they're sharp. They're like SVG. They're like vector graphics. It's like that. As if they patched on top of it.
I wish I had your eyesight. To me, they still look blurry a little bit on
Yeah, yeah.
Okay.
The rest is blurry. The squares stand out.
the middle part. Yeah, okay, I see.
Yeah, this first stands out a lot.
How can you reconstruct them that perfectly? I'm just wondering. Maybe that's a property, but I don't know.
You doubt it?
Yeah.
Well, in common foods itself, I'll not be surprised for linear systems. But this, I don't know. I'm blind. I don't know. I don't know. I don't know if it's a.
Yeah.
Yeah.
Okay. Anyways.
Anyway, so that's what that is. For the second one, it's more about so you have these images, right? And then you apply these control actions to it, right? You rotate it to the left, rotate to right, and see how well the model changes, the output of the model changes, right? The state. So the output of the model is the latent space, the latent state that you don't have, right? That's what you're predicting. You do have the observations here. There are no observations in the second row, right? So all you have is just you got these images, you clean images, you feed them to the model with specific controls. So you want to rotate small, rotate to the right, rotate to the left, small, no rotation, blah, blah, blah. So you read from the bottom up, and then you have no rotation, these are the actual figures, and then you do a large rotation to the left and see how the model state changes. So that's what it is. They just wanted to show, kind of give an intuition that the rotations, the model cares about the control as well, and it's not just the states. That's what they want to show. And then here to the right, the last figure, they have the first row is noisy images. Oh. Sorry?
The row or the column? The last one.
First column. First column is noisy images that the model has not seen. Right? So the model hasn't seen these, right? And it's trying to use the model to create the model itself to predict what the states will be from the noisy measurements, and then they apply the control units, control actions, try to see if it rotates, and blah, blah, blah. So right here, the first column is the noisy stuff. You can see that some of them is good, like this one. So Sergey, are you happy? No?
It's a 5, right?
Well, it's supposed to be a 1, no?
Yeah.
Yeah, so.
And it likes 5s everywhere.
It seems like a lot of 5s, yes. Like here.
And the bottom one.
The bottom one? Oh yeah, the rotation. Yeah.
Maybe
so, yeah.
it's overfitting on 5s a little bit.
Sorry, say that again.
Is it overfitting on 5s? Like it's replicating 5 instead of looking at what it is. Is that?
Well, but the rotation is getting correctly.
Oh yeah.
Sorry, the what?
Yeah, never mind. That's a good point.
So, what do you rotation? Well, yeah, the rotation is I mean That's a much easier task, I think. So maybe have a model that you change something good. Maybe it's not that easy. I'm just thinking that's easy because it's a. No, it's not that easy. This is images. It's not. Yeah.
Well, but they're vectorized in a single vector, right? To how to what is the sequence there? Like entire image is a sample at one time point, right?
Yes.
And they're just different noises
Yes.
are adding
Yes.
at each time.
Yes. Exactly.
So like in the first example, reconstruction during training, you have just one image and multiple instances of noise of that
Yes.
image. So it's static, it's not moving,
Yes.
but we have multiple observations.
Yes.
So it's
So, yes.
averaging out the noise in
Exactly.
that sense.
Yes. Yes. In that sense. Yes.
But then it starts moving.
Mhm.
Yeah, but the
Yeah.
same thing
Yeah.
with the noise.
All right.
And is it offline? Like, is it
This.
does it have a chance to correct backward by knowing what's in what was like hidden Markov model would do, right?
Yes. Yeah. True.
but,
No. No. They don't mention that. No. No.
Just one.
But correcting backwards is kind of interesting.
Well, it's like if you made a prediction, but then you saw something in the future. Oh no! Like we have
There's
to
a-
correct
yeah, yeah.
everything. The trajectory is actually different.
But I guess that's gonna work for more offline cases, right?
Yeah. Well,
Yeah.
I mean, yeah. Only.
Only, right. That kind of does make a lot of sense. Because the more data you see, the better the model becomes, right? So it makes sense to come back and then readjust.
Yeah, by the way, Kalman filter is a standard thing in the electrical engineering curriculum. If you don't know Kalman filter, it's good for your soul. I highly recommend to actually get familiar with this guy. Kalman filter, hidden Markov models, and then in general, Fourier transform, wavelets, and all that stuff. It's just you become better.
All Sergey is saying is come slow, talk slow.
Okay, well, we need to quiz you then. Are you certified?
I'm not. I never took that certification. It's like, I'm gonna leave down anyway. It's just probably gonna be useful.
It's like if you tell the story of Fourier transform in the wrong way, you're gonna mislead people for the rest of their life.
Really?
Yeah.
The story itself?
No, I mean
Oh,
Fourier
you mean?
transform.
Oh, yes, definitely.
What it is.
Oh man, everything is doomed without Fourier transform. Anyway.
Yeah, that's a T-shirt. Okay, good.
Alright, so these are samples from models trained with so trained from different models. As we mentioned, I'm not exactly sure which model they use for this one. Which one? I think I missed it. This
I didn't see a mouse again.
one. Was that?
I didn't see a mouse again.
No, this whole page.
Oh,
I'm
this
not
whole
sure.
page.
Yeah, I don't. I maybe
Oh,
I
you
missed
don't know
it.
which one they use.
Yeah, but they compared it for this one. Right, and they looked at the log likelihood and then just made a claim that the the bidirectional recurrent neural networks kind of work best, and followed by QLR, which looks at the what is it? It looks at the previous, the current, and then one future point and from. So that was about it. Which I personally think it does make sense. But I was kind of hoping that the QRNN might outperform the QLR.
I mean, eventually they line up, right? At least.
So it's not that different.
After no, with training, see at 500
Oh.
stuff, they
Oh yes.
like independent is not learning, it's saturated. But,
Yes. Okay.
but RNN is a little like keeps learning, and even though LR is a little bit like above, but then
It
catches up
Okay.
very slowly.
Okay. Do we know why? Do we know why that? Do you have any reason why that? Okay.
So what again? LR is doing. LR is just looking at the nearest neighbors in control.
Yes,
Right?
nearest neighbors. So
Well,
on it back.
maybe that's enough.
Maybe it's just a simpler model which trains faster. But
That's
eventually RNN. Which is
okay.
not perform.
Okay. Oh, yeah, that makes sense.
Also, maybe well, It's like there are no sudden jumps in the trajectory or measurements of the trajectory, so that everything is smooth. A Markov in that sense, that knowing the previous one is enough, and the next one. So I think it's some smoothness property of the model of the simulation, the data. It's really enough to be more enough.
See this, so this is supposed to be the actual medical data set, but I didn't get a chance to look at it, so I don't even know. I don't know. I can't explain what is going on in the B and the C part, but the output, sorry, the A part is no. So I really don't know. I don't know. I didn't. I couldn't take a look at it.
So I guess I'm kind of confused, like what is the state again? So like you have for this, you have like a sequence of images of one digit and like they're rotated, and then the thing is trained by like reconstruction. Then they throw away the decoder, and then they want to estimate the state, right? What is the state? It would be like rotation to the right, rotation to the left, or something.
Okay, so
The
this.
sequence of rotations.
Okay, so the state should I use? Should I use maybe fMRI? Can I use brain?
Yeah.
Okay, so fMRI captures blood flow. You don't care about blood flow. You care about how the brain works, right? Which is how neurons activate. That's what you care about. Which, well, is hard to get that. So what you can measure is a noisy estimation of that, which is blood flow, right? So given blood flow, can we predict the actual neuronal pattern, for instance? So that actual thing is the state that we're trying to predict.
Oh, okay.
Right, but that's a stretch. That's a stretch because blood flow is not noisy measurements of neuronal activity. It's a very non-linearly mapped process. So that's not what Kalman was give you. So imagine that you have a car, in space, there's a plane that's moving. You want to know exactly where it is so you can kind of help.
Elon Musk's car.
Yeah, right. Yeah, exactly. You want to know what a car is, so you can kind of like give what the plane is, so you can give the pilot instructions where to go if he's lost, right? But if you don't know where he is, what do you do? But you have measurements. The measurements are noisy, right? So what can we do? Let's try to predict what he is, where he actually is, given the noisy measurement that we have. So we have bad data. We know that the good stuff is in it somehow, right? Let's try to get it, right? And that good thing is what we call the state. And then
well, it's XYZ location.
Yes.
In some coordinate system.
Yes, exactly. And then the rotation is that, well, the plane is not just moving; it's moving because of something. If it's this car, you got gas in it. It depends on how hard you press on the accelerator. It depends on how you move the steering wheel. So where it is depends on all these things as well. So you need to know how those things control the movement as well to be able to give a better description of what the model is. You can't take those things out and know where the plane is. You can't, right? Because if the plane is moving to the left, you have to know that the guy is going to the left, so that you can predict that. Oh, this is where it's going to be, right? But if you don't have it, then
So it's like a trajectory estimate. That's kind of what
Yes.
the latent space is. I guess for this,
Kind of all of the parameters of the model.
Mhm.
The values of the parameters of the model. Well,
I don't know. I'm thinking like, what is the interpretation for this in this example? Like, what is the interpretation of?
the state is the angle of rotation and then the value of each pixel of the true value of each pixel. That will be the state. Or no, I mean, because when you know the value of each pixel, then you don't need a rotation. It's kind of.
You do the first one because you can the one with the spaceship. You use that one. So you know the.
Oh yeah, that.
Yeah, so we have actual true versus
Yeah.
observed. Yeah, but we don't. So.
Well, with the spaceship, it's easy. You have some kind of polar coordinate system. I don't know.
Yeah.
You can some kind of coordinate system that you can, I don't know, Geocentric.
But this is when we can't know it, so, cause it's the late variable, I think, so yeah.
Oh, but I guess it's like a distribution from which you can draw samples.
No, the state is like the real thing.
Oh,
Say it's like now we're getting into the philosophy, Platonic, or like there is a real thing and there is noisy observation of that thing.
hmm,
So, but the real thing is described by some variables.
Hmm.
What are those variables? So,
Yeah.
like with the spaceship, it's location coordinates.
I guess I'm thinking like after you train the model and then you just like throw away the decoders. What would you like? What would be the output if you provided input to the trained encoder? Like, what would be the actual output for a sample? I guess like just the actual angle rotations for the image.
You get
Because I'm trying to think like how this would work with fMRI.
okay.
But it's okay. Maybe it's too
No,
much.
no, it's not. It's not too much. So here we have an input, right? Right here. This one.
This is measurement.
Yes, measurement. Right. So you measure it. You have a measurement, right? This is what you have, fMRI data. You know that it's something like this. How do you get it? So the model gives you this, given this input.
Mhm. Yeah.
Does that make sense?
Mhm.
Right? Does that make sense?
So it's
Yeah.
in this case, it's very much maps to what are the value of actual pixels given your noisy observations, multiple, not just one, like
Yeah.
multiple noisy observations of the same thing. You know that those pixels are not like they're true in the sense that their value is fixed. They have a state. They have a fixed value of each pixel, and so that's what you're trying to recover. This value of those pixels.
So that is a simple example. And then here, right here, given, let's use a good example. This one, given this input, no, let's use a noise one. Yes, this one. Given this input, right, which is noisy, the output that the measure, the thing that we get, if we put this input there with a rotation of say 5 degrees, what do we get? And that's what it's gonna be. Oh my god, this stinks.
The mouse.
Yeah,
Oh, yeah.
so if you have this noise, this noisy data,
Yeah.
right, and then give this to the model, and then we know that the control that we applied to the model,
The rotation.
which is the rotation,
Okay.
we rotated by 5 degrees. But this is the input. We know that the rotation is 5. What does the output look like? And we get this. So the point is that we want to know if this person, like to have a patient, right? We know we have the person's both signals. We measure fMRI. It's noisy, just like this. We gave the person 5 doses of a certain, CBC, whatever, schizophrenia, CBC, something like that. What does the brain look like after we give them that medication? It looks like this.
Oh, okay.
That's what the output of the model gives us. So that's the intuition behind it.
That's cool.
Yeah, that's really cool.
There's a lot of application to do with that. Okay, cool.
Yes, that's what Pavel is trying to do.
That's what I'm trying to do.
Well, I've been doing a lot of these kinds of things, but I find a weird way to do everything without so I have to try to, I need more intuition why I need deep learning. Because most of the things that I do, somebody might do with deep learning, but I usually get away with the classical physics stuff.
You don't need deep learning, yeah, it's for everything.
But I wanna, because everybody's talking about it.
No, but this is a very good example. Yeah, TJ is comes right. Yeah, if you can do it with logistic regression, don't do it with.
Yeah, because in a project that I'm working on, I'm basically trying to do this, but what I do is that, even if it's less. So it's kind of like one of the things that you could do is that for each, you have a temporal sequence, right? And then you're saying that the dynamics are not linear, for instance, but you kind of approximate the system linear at short time scales. So like you have a
locally linearized.
Yeah, so that's what I basically like you have a sine wave. This is a non-linear. Everybody knows it. You can fit several linear lines to it, and then you can approximate it. So if you take a very short time scale, you can fit a line to it, and then just fit another line, and then you can know what the dynamics look like here, what it looks like here, and you have a time varying linear system. So that's basically what I have been working on this year. It's cool. I like it. Like I use Koopman operators to get that, and then I do recursive least-squares to propagate and find the A time varying A and use that. So and Pablo does something very similar, but he used deep learning. It's very similar, practically the same thing, but he uses deep learning. So I just thought it was cool.
So it's like a Newton. So it's like Newtonian physics and Bohr. So he's more Bohr kind of
Yeah,
energy,
yeah.
and you're
I would take Newton any day. Yeah, but that's
No,
the
but think of this sinusoid example. Like I'm with you that yeah, you can use simple method, but it depends on like on the past because when you know it's a sinusoid, then it's easier for you to think about circular motion and cycles
yes.
and rotations
Yes.
and things like that. So you're kind of abstracting away from this
Yes.
little scale and going to a new
Yes.
level. I don't think deep learning can help you with that, but
Okay.
I'm just saying like where there's
Mm.
no understanding of linearity,
Right,
that the
right.
system is not linear,
Right.
can take you further than
Right.
just I'm locally linear and I'm fine, I can
Mm.
predict, but then maybe you don't understand.
You don't. Yeah. True. It's true. I agree.
Just something like that. But this is a good also example which common filtering is good. Okay, go ahead.
Which is good. Yes, Kalman filtering still allows us for the inclusion of control inputs, which like typical RNN wouldn't. So this allows us to have.
RNN is just the generalization of the same idea. It's a dynamical system. RNNs are general dynamical systems.
They want to show that their proposed date is different from RNN, so like but it's like, well, they're the same thing. You just added a new block to it that the model sees. That's all. But I get what you're saying. So, but they just want to say, well, ours is different from RNN, but it's like, no, it's the same thing. You just added a new unit to it. That's all. Yeah, and then you compare system dynamics from learned model parameters. That's what Pablo is doing that I like so much. I've been talking about it the whole time. And then join me. Let's do some dynamics. Yeah.
I have one question. At the very earlier in the slide, like way towards the beginning, you said they generate the sample. What do they use to generate the sample? I think I was a little confused about that. I didn't quite understand it. I just want to make sure I get that. It was after this, I think, because it was when they're proposing the because you said it was at the point where you were saying that the model generates a new sample, so they can use that instead of it was after this too, I think.
Would you remember?
Well, if you go up, back,
I think it was this part, the general model. How do they generate that? I was just kind of confused about that.
The recognition model?
Yes, because it sounds like what they're doing is it's a test. It's testing itself, right? So is it just like a typical testing data? I'm just curious about that. Sorry.
No, I think I'm not getting.
Sorry, it's like so? How do they generate the? So it's like a test model. Are they like the test data set? Is that what it's doing? I'm trying to make sure I understand how it's correcting itself if we can't observe it.
No, it's using observational data. There is no sampling there.
Oh, okay.
You can sample.
That's what I was wondering.
Yeah,
Sorry.
you can sample
Oh, okay. Okay. Sorry.
if you want it, but you're sampling in the same weird way as variational encoders do and things like that. It's basically you're generating the mean and covariance deterministically. It's a function mapping, but then you sample from that distribution by invoking your traditional uniform random number generator, map it to Gaussian data, blah blah blah.
I get it. So it's like, yeah. For some reason, I thought it was bootstrapping. My bad. Okay, thanks.
No, yeah, there is no
bootstrapping. Yeah.
Kalman filters, or not Kalman filters. Particle filters are a very general version of this. Yeah, it doesn't require Gaussianity. It doesn't require and it is not linear and doesn't use deep learning. So, but it uses sampling and it's considered oversampling is bad. It's very computationally inefficient. But I don't know if that's true now with all of this parallel, like you can sample on GPUs and large methods.
I guess at the time where they were filmed, they didn't have all these things that we have. So Kind of makes
Yeah.
sense.
But the good thing is, can you go like slowly towards the beginning?
Okay.
Here.
Okay.
No, one more. Sorry. Here, deep Kalman filters.
Mhm.
So I think this covers a huge. I don't know what I'm afraid to put percentage, but a huge amount of how deep learning is used in the natural world, kind of where it's applied.
Mhm.
Uh, Neural networks are fitting, right? Function approximator,
Mhm.
like very good function approximator.
Mhm.
So, like this is a good example. You had a function, and then you said, "Oh, let's replace this function with a neural network," because here we're too strict. A times A plus B, it's linear function, very constrained. We can compute it easily, and it's clear to us, but it's too strict. If we start adding Fourier terms or something like higher level, that's not general and that's also restricted. So let's just stick a neural network and let it learn that function.
Right.
And that's how in many success. Well, think about nerves, the reconstruction of 3D scenes from images, light field. We don't know how to compute it. Oh, stick an MLB there and it will learn. And yes, successful. So a lot of success stories in application. At least I cannot come up on the fly with any example where it is not like that. It's just replace what used to be done either by human intuition, like initial values and things like that, or by a rigid, clearly wrong, but something that we can handle model.
Right.
Just replace it with neural network, train it, and neural network encodes some mapping.
Right.
So the bottom one is a good example. Like neural ODE, differential equations, right? It's the same. Oh, let's say that the velocity derivative x is a function of x.
Yeah.
Some function. Oh, neural network function.
Right.
And that's it. And now we got a differential equation with neural network, and let's just solve it. Train it first.
Right. Right. My problem has been that most of the time we care about that f. We want to understand that f, which I think that the neural networks don't give us, right? Because
Depends, but what do you mean understand?
Well, well, so for instance, what the difference between what I think I'm doing and what Pavel is doing is that
Pavel doesn't understand anything. I'm just. Here comes explosion.
the point is
I don't expect his stable. He's not. I don't think he's going to explode. He's a stabilized.
So, for instance, I can take a look at the F, right, and see that at this point in time, the system behaves like this. Like the system is oscillating. At this point it's more stable. At this point, if you add just a little bit amount of control, it explodes, right? Whereas I can't necessarily learn that from the system when I use deep learning. I can only do a lot of input, output to try to figure out what it is.
The first thing that you just described, or how do you actually do that?
It's about 200 years of stability theory.
Yeah, it's control system.
Frobenius prawn theorems and all of that.
I take the Jacobians of that. You can do a lot.
And I can compute eigenvalues and see if they're like all that.
Yeah.
Just quick question off topic. TJ, can you hear us well? Because we moved here, the microphones don't work in the other room.
Yes, I can hear you.
Oh, okay. So the sound is at least good here. So good.
Yes, I can hear you guys great. It's a lot better than the other room.
Oh, maybe it's just Lord has better articulation.
There's less space, and that's it.
Yeah. Well, okay, good. So let's keep it here for now until they fix the microphones. Okay, I think that was informative. And if you didn't know what Kalman filter, there's an unscented Kalman filter before you jump to particle filter.
Yes.
Yes. It's an interesting
I've
field.
implemented some of those.
Yeah. They still work on particle filters. Some
Unscented?
as well. No, particle filters.
Okay.
Now is still an interesting field. We're trying to optimize this.
IC papers from now.
Okay.
Okay, then I think any more questions? Comments? Yeah, thanks. Have a great Friday as well, TJ.
Good job.
And online people.
Hey, how many got us up?